Welcome students. Dear students, in the previous video lecture, we discussed about the basic concepts of polarization of light and doubly refracting crystals, and also we cover the Huygens construction of ordinary and extraordinary rays. In this video lecture, I am going to explain the optic axis in the plane of incidence and inclined to the crystal surface, that means refracting surface of the crystal. Here there are two cases arises. One is oblique incidence and second one is normal incidence. Here we shall discuss about the first case, the oblique incidence. See here in this diagram, let PQ is the surface of the negative crystal. Here negative crystal means, we already discussed in the previous video, the refractive index of ordinary ray greater than the refractive index of extraordinary ray, then the velocity of ordinary ray less than the velocity of extraordinary ray. Such a type of crystal is said to be negative crystal. For example, is tourmaline crystal, ruby, emerald, sapphire, calcite and apatite crystals are negative crystals. See here in this diagram, PQ is the surface of negative crystal. PQ is the surface of negative crystal. AB is the plane wavefront. Here AB is the plane wavefront. A is the source of two secondary wavelets, and O indicates the secondary spherical wavefront for the ordinary ray, and E indicates the secondary ellipsoidal wave front for the extraordinary rays, this one elliptically shaped. Here CM is the tangent drawn at the point O, drawn at the point M on the ordinary wavefront, and Cn is the tangent drawn at the point N on the extraordinary ray. Here let T be the time during which the incident wavefront reaches from B to C, so that the time of interval T equals Bc upon the speed of light, that means V, velocity of light, that is in air. During the time of interval T, the ordinary ray traveling a distance AM, shown here, with a velocity V0 inside the crystal. Here V0 means it is the velocity of ordinary ray, that is T equals AM by V0, AM by the velocity of ordinary ray. Therefore BC upon V equals AM by V0. That means AM equals, on further simplification of this one, we get BC upon V into the velocity of ordinary ray. This is equal to BC by refractive index of ordinary ray, because the refractive index of ordinary ray is given by the formula the velocity of light in air to the velocity of light in the medium, nothing but velocity of ordinary ray. This is velocity of ordinary ray inside the crystal. This is according to the definition of absolute, so relative refractive index, where n naught, that means refractive index of ordinary ray. See here, if Ve is the velocity of extraordinary ray along an, this one, an, then the time of interval t is given by the formula an upon Ve. An means distance traveled by the light, that means it covers a distance an inside the crystal upon velocity of extraordinary ray. From these two equations, here an by Ve equals Bc by V. On further simplification, we get an equals Bc by V into Ve. This is equal to Bc by Ne, because V by Ve is nothing but refractive index of extraordinary ray. Ne means velocity of light in air to the velocity of light inside the crystal. That means velocity of extraordinary ray, this one, along an, where n is the refractive index of extraordinary ray. Am is the radius of the ordinary spherical wavefront. Here in this diagram, Am is the radius of ordinary spherical wavefront for ordinary wavefront. The extraordinary ellipsoidal wavefront has the semi-minor axis along the optic axis AD. Here this one, xy is the optic axis of the crystal, AD is the semi-minor axis. Semi-major axis AG, here AG, at right angles to the optic axis. Here AG is perpendicular to xy. xy is the optic axis of the crystal. Therefore, the spherical sphere drawn with A as center and AD equals BC upon refractive index of ordinary ray. BC upon refractive index of ordinary ray, as the radius represents the ordinary wave surface. Radius AD represents the ordinary wave surface. Therefore, the ellipsoidal drawn with AD equals BC upon refractive index of ordinary ray as the semi-minor axis, and AG equals BC upon Ne. Ne means refractive index of extraordinary ray, as the semi-major axis represent an extraordinary wave surface, where Ne is the principal refractive index for the extraordinary ray, and in this case refractive index of extraordinary ray, this means principal refractive index of extraordinary ray, which is less than refractive index of extraordinary ray and also less than refractive index of ordinary ray. Particularly, Ne stands for principal refractive index for the extraordinary ray. Thus, the ordinary and extraordinary ray travel in different directions with different velocities. Here, this one is the ordinary ray path, this one is extraordinary ray path. Hence, they both ordinary and extraordinary rays travel in different directions with different velocities. The ordinary ray AO is perpendicular to the tangent CM. The sphere where the extraordinary ray AE is not perpendicular to the tangent CN, to the ellipsoidal. Let us discuss the second case, normal incidence. See the diagram. Let AB with a plane wavefront, AB with a plane wavefront which is incident normally on the surface PQ, on the surface PQ of the negative crystal. The incident wavefront AB is parallel both before and after refraction. Before and after refraction. Here the incident wavefront AB, here AB is parallel both before and after refraction. Let Mn, here Mn shown here is refracted wavefront, is the refracted wavefront tangential to the spherical wavefront of ordinary ray, and RS here RS is the refracted wavefront tangential to the ellipsoidal wavefront of extraordinary rays. ಇಲ್ಲಿ ಆರ್ ಎಸ್ ಅನ್ನೋದು ಟ್ಯಾಂಜೆಂಟ್ ಅನ್ನು ಎಳೆದುಕೊಂಡಿದ್ದೀವಿ. ಇಲ್ಲಿ ಎಲಿಪ್ಸಾಯ್ಡಲ್ ವೇವ್ ಫ್ರಂಟ್ ಏನಿದೆ ಎರಡು ಕಡೆ ಇದಕ್ಕೆ. ಇಲ್ಲಿ ಎ ಬಿ ಅನ್ನೋದು ವೇವ್ ಫ್ರಂಟ್, ಇದು ಪ್ಯಾರಲಲ್ ಟು ದ ಆಕ್ಸಿಸ್ ಪಿ ಕ್ಯೂ. ಬೋತ್ ಆರ್ಡಿನರಿ ಅಂಡ್ ಎಕ್ಸ್ಟ್ರಾರ್ಡಿನರಿ ವೇವ್ ಫ್ರಂಟ್ಸ್ MN and RS, MN for ordinary ray, RS for extraordinary waves, which are parallel to the refracting surface PQ. Since AO is perpendicular to MN, here AO is perpendicular to MN, and AC is not perpendicular to RS. AC is not perpendicular to RS. The ordinary and extraordinary rays travel along different directions. Here AO is perpendicular to MN, and AE is not perpendicular to RS. AE is not perpendicular to RS. The ordinary and extraordinary rays travel along different directions. Here ordinary and extraordinary ray, in both the cases ordinary and extraordinary, they travel along different directions. This is about normal incidence. Let us see the second one. The optic axis in the plane of incidence and parallel to the refracting surface. See here, optic axis in the plane of incidence and parallel to the refracting surface of the crystal. In this situation, there are two cases arises. First one for oblique incidence of wavefront. Second case is for normal incidence of wavefront. Let us see the first case, oblique incidence. Let AB is the plane wavefront incident obliquely on the refracting surface PQ, of the negative crystal. The optic axis in the plane of incidence is parallel to the PQ. The optic axis and the plane of incidence is parallel to PQ. The refracted spherical and the ellipsoidal wave surfaces touch each other along the line PQ. That is optic axis, shown here. Therefore, The ordinary and extraordinary rays travel with different velocities in different directions. For this situation, we can derive the value of AM for ordinary and value of AN for extraordinary. You can derive as I already explained in the previous slide. Ditto explanation is required here, but I can't show in this case in this slide. Hence, you can refer the same derivative part by starting with time of interval t equals AM by V naught for ordinary ray, and time of interval t equals AN by VE, velocity of extraordinary ray for extraordinary ray. We can get finally the semi-minor axis of the ellipsoidal is equal to AM, that is BC upon refractive index of ordinary ray. The same way, the semi-major axis of the ellipsoidal equals AN equal to AN, semi-major axis equal to AN equals BC upon refractive index, principal refractive index for extraordinary ray, BC by NE, capital E. Here NE stands for principal refractive index for extraordinary ray. Hence, we conclude that the principal refractive index for extraordinary ray, which is less than the refractive index of extraordinary ray, and also less than the refractive index of ordinary ray. The ordinary ray obeys the ordinary laws of refraction, whereas extraordinary ray does not obey, since its velocity varies with directions. Both the rays are plane polarized. Both the ordinary and extraordinary rays are plane polarized. Second case, normal incidence. For normal incidence, let AB is the wavefront which is incident normally on the refracting surface PQ of negative crystal. Here the optic axis in the plane of incidence and parallel to the crystal surface PQ. MN, here tangent drawn on both spherical wavefronts of ordinary ray, that is MN is refracted wavefront tangential to the spherical wavefront of ordinary ray, and RS, here RS is the refracted wavefront tangential to the ellipsoidal wavefront of extraordinary rays. In this case, both the wavefronts MN and RS are parallel to the refracting surface. Both MN and RS are parallel to the refracting surface PQ. AO and AE are ordinary and extraordinary rays, both traveling along the same direction with different velocities. See here, AO and AE, both ordinary and extraordinary rays traveling along the same direction with different velocities. Therefore, a definite path difference is introduced between the ordinary ray and extraordinary rays. This principle is used in the construction of quarter wave and half wave plates. That's all. Thank you.